be a semi-autonomous rover building autonomous capability as it goes for a 14 Earth Day or 1 Lunar Day. The last one I'll kind of highlight, and I could talk about the technical challenges and how we're planning to overcome them for climate change and agriculture. All of that is due to space and space investment.
Maybe not a very funny one, but we have to talk about it.
We're not going to collect the material, bring it back, and then sell it on Earth, because the value, as I mentioned about in situ research utilization, is using it where you find it.
Welcome back on the Space Info podcast. Here we talk about space and everything related to it. If you are passionate about space, astronomy, technology and everything about it, you can join all our social platforms at the Space Info Club or our website at www.spaceinfo.club, where tons of content and a community of experts are there waiting for you. This is the Space Info Club. Good morning, everyone. Today we have a very special guest here on the Space Info Club podcast. Joseph Kenrick is a program manager at Lunar Outpost Oceania, based in Melbourne, Australia, and he holds a master's degree in space resources and a bachelor's degree in petroleum engineering with a minor also in economics from the Colorado School of Mines. Well, Joseph worked as a reservoir and production engineer in the oil and gas industry for several years before transitioning to the space industry. During his master's studies, Joseph conducted research on mining water and regolith on the lunar surface. So maybe you are understanding the topic of today. And during his master's study, Joseph conducted research on mining water, as I said, and also regolith. So at Lunar Outpost, he played a vital role in various advanced rover projects, such as NASA's Break the Ice Challenge. Currently, Joseph is spearheading the Hilo 2 Consortium's technical and project effort as technical director to develop an autonomous lunar excavator for the Australian Space Agency Trailblazer program, which will be the country's first rover mission to the moon. And also Joseph leads the commercialization of the company's space robotic systems for use in extreme environments here on Earth, on our planet. So good morning, Joseph, how are you?
Good morning. Thank you very much for having me, Sebastiano. I'm pretty excited to talk to you about what we've been up to.
Me too. So thanks for being here. And well, I would start with something that people are very curious about. I'm talking about the Trailblazer program, and I would like to talk with you about the objectives of the mission and the scope of it.
Yeah, great place to start. So the Australian Space Agency's Trailblazer mission is an initiative that fits under the Moon to Mars initiative. So there's a couple sort of key pillars within that initiative, and the Trailblazer program is set to be Australia's first lunar rover. So overall, this is a partnership with NASA, where NASA will supply the rocket and the Eclipse lander. We'll do the procurement for that, and Australia, through the Australian Space Agency, will supply the rover. So the mission objective is to go to the lunar South Pole later this decade, hopefully around 2027 or 2028. It will be a semi-autonomous rover building autonomous capability as it goes for a 14 Earth Day or 1 Lunar Day mission, where it will be collecting samples of regolith, analyzing it, looking for volatile contents within the regolith, trying to understand the Eclipse lander's impact on natural and or implanted volatiles that may be present, and overall increasing our understanding of the lunar South Pole, potential resources, and again, lander's effects on it. So this can really help inform future in situ resource utilization or ISRU missions for the Artemis program and the global space community.
Yeah, so basically this, a lot of people maybe are thinking about, okay, so we are going to the moon to explore the surface and also the little layers that are below that surface. And yeah, you mentioned the South Pole, and which is, let's say, becoming very crowded with people and companies that would like to reach that zone, because is the, let's say, the very first one we are aiming to for also future human exploration. But yeah, for what it may seem easy, I think that there are a lot of technical challenges and also innovation that we can, let's say, take out from these challenges? Also, you mentioned the fact that the rover will be of a semi-autonomous kind. Maybe you'd like to clarify a little of what do you mean with semi-autonomous?
Yeah, so I'll kind of work backwards there. It's autonomy in these environments is extremely difficult. For starters, there's no GPS, so all of your localization needs to be done on local sort of features. So you use your camera systems to identify objects. It could be the terrain, the mountains in the background, or local say boulders or craters, and use those to identify its position in sort of space, and or the lander is always a good fixed sort of reference. So that's either visual based, you have your wheel odometry and IMUs to measure sort of your acceleration and change of position as you start to move, and you reconcile all that to again give you a hopefully accurate position of the rover within 3D space on the moon. And once you have a solid position, you can start to do path planning, and then it can autonomously sort of execute on a plan. That becomes extremely important as we start to go into space, particularly because of the round trip speed of light. When you're talking about the moon, it's about 7 seconds between sending a command for the rover to receive the command and then sort of confirmation that it came back. When you're looking at Mars, it could be something like 20 minutes. So you really can't rely on an operator, sort of line of sight, just driving through the video stream. So you have to become reliant on autonomy as you start to get more and more complex tasks. And as you said, there's a lot of interest in the South Pole, so hopefully there'll be many rovers there soon, and you'll want them to sort of autonomously work together, particularly to ensure that they aren't potentially damaging things like running into the lander. So it needs to be autonomously identifying those and executing prior to sort of the human response kicking in. So our autonomy systems are looking at the path planning, looking at actually executing drives, but also some of the excavation. You mentioned some of the just technical challenges more broadly. What's really exciting about this mission is the excavation component. Later this year, Lunar Outpost is sending the first commercial rover to the moon. But another first for this mission is really the space resources and excavation side of it. We haven't done autonomous rover excavation on the moon before, so it's a new element, and that comes with a lot of challenges because every large sort of mining or excavation system on Earth is really gets the force that it needs from the weight of the vehicle itself. But when you're on the moon, your weight is immediately cut by 1/6 due to the lower gravity, and we're heavily constrained on the amount of mass that we can send. The Trailblazer rover is limited to 20 kilograms, so it's effectively about 3 kilograms on Earth, which means it's really hard to dig deep into the ground. So that's an added element. The last one I'll kind of highlight, and I could talk about the technical challenges and how we're planning to overcome them for a while, but being the lunar South Pole means you have really extreme lighting conditions. The moon is almost a perfect top, so it kind of spins around, and the sun is just going around the horizon, never going above about 10 degrees above the horizon. So you're always in an extremely long shadow and sort of black or white visual scenario. So camera systems aren't really tuned to that sort of environment, or cameras for Earth. So you need to do a lot of testing, which we've been doing over the past year to sort of replicate that appropriate albedo, which is the reflectance of the lunar surface in that extreme lighting condition.
Yeah, indeed. I think that something that we could, let's say, underline for the difficulty, and also again under the semi-autonomous aspect for the people who are listening. Well, think about the difficulty that we are experiencing here on Earth while trying to build autonomous vehicle, autonomous car. Well, we have a lot more confidence, a lot of more, let's say, resources, for example, GPS, that we have available here on the planet, but it's not available for sure on the moon. And by instance, China has said that they will try to put a constellation to give reference to their astronauts and their rover on the surface of the moon. So this just gives the idea of the tremendous difficulty that we have to face when trying to build such kind of system. So maybe also the idea of collaborating with other companies and also other agency has to be considered. So maybe you'd like to tell us if your partnership in the introduction we mentioned NASA, so maybe you'd like to tell us a little more about your partnerships and collaboration.
Yeah, it's a great question. We have a really good sort of saying within our consortium that if you want to go fast, go alone. If you want to go far, go together. So this is very much a team effort within sort of our consortium, which is called ELO2, which is the group that's actually executing on some of this work, but even the collaboration with the Australian Space Agency to ensure this is successful, and then the broader collaboration with NASA. There's sort of collaboration on really every level, from sovereign to sovereign and then company to company. So let me take one step back before I explain all the partners.
Sure.
I've explained the Trailblazer mission, but let me explain sort of the program. So the Australian Space Agency's put together a 2-stage program. So we actually just finished, as of pretty much today, stage 1, where there was 2 consortium competing to build the eventual rover, which the Australian public calls Rover. There was a public vote. That's the name that they decided on. So we'll decide, the winner of stage 2 will be decided probably in the next month or so, and then we would move on to then build that rover, which will be the real one that goes up. So in stage 2, our consortium is called ELO2, which stands for EPE and Lunar Outpost Oceania Consortium. So I work for Lunar Outpost Oceania. We are the technical leads, but our co-lead is EPE Oceania. They're a defense robotics company. They're based in Brisbane and we're based in Melbourne. But we also have 19 other consortium partners. So I'll run through the list pretty quick, but we have some industry partners in BHP, mining company. We have Element Robotics, Innovore Technologies, Sabre Astronautics, Titomic, Vipac. Let's see, and then we have many university partners. We have RMIT, University of Melbourne, University of Adelaide, Australian National University, Swinburne, Monash, University of Sydney, and their Australian Centre for Field Robotics Group, and Queensland University of Technology, University of Tasmania, and Edith Cowan University. And then our one US partner is Colorado School of Mines. And then we have outreach partners and One Giant Leap Foundation Australia and VSAC, which is the Victorian Space Science Education Centre. So a lot of partners, but they all have sort of specific roles within the consortium and all have complementary efforts. And we want to, through this, not just deliver Australia's first lunar rover and a successful mission. It's about building industry capability in Australia, advancing research, and advancing the STEM education goals for the country. Generating that interest in young kids and older to show them that there are career pathways in this and generate sort of job avenues. So that's why we have such a wide range of partners there. Again, from anything from education and outreach to helping us manufacture the rover.
Yeah, I really like the fact that you mentioned a lot of partners. And one question that came to my mind while we were talking, particularly in the end when you said, okay, our common goal, clearly your common goal is delivery Australia a first lunar rover. But in my mind I was thinking, okay, but since you mentioned such different kind of partners like university and private companies and then agencies, everyone has a different role. But I think that even though the final goal is a single, is one, I think that let's say the intermediate goal can be different. So probably every different stakeholder is driven by different purposes, at least in the intermediate steps. So how is there any difference in approaching a different kind of partners in this kind of job?
Yeah, I think what can kind of provide a little more context into the different sort of goals and then the partners we chose is the pillars that the Australian Space Agency has sort of outlined for Trailblazer more explicitly. So there's the technical pillar, which is basically designing and delivering the rover to the best of the capability. There's the programmatic pillar, which is more your capability to do that. So that is really where the team comes in. Do you have the capacity to actually design and then build and then run the mission with appropriate quality assurance and risk management sort of strategies. The other two are then commercialization. So they want to see that this technology has dual use capability and is impacting secondary, tertiary markets and is not just a one-off. It's essentially grant funding that it turns into R&D that enables commercialization of this technology for the future to create sustainable businesses. And then the last pillar is on inspiration and industry impact. So that's where we want to, there's a bit of overlap there, build the industry, but also bring the country along with us and sort of inspire the nation and again, generate career pathways for students in Australia and across the world. So those are the four sort of criteria upon which we're measured in stage one and are the key pillars sort of moving forward. So with those in mind, that's how we sort of went about designing our team. And some members are really sort of focused on, say, the commercialization pillar. Some are really focused on the outreach pillar, and some sort of spread across all of them. As technical lead at Lunar Outpost Oceania, we obviously are heading up the technical pillar, but really have our foot pretty heavily in all of them. So that's where those came in, and then obviously the relationship we have with each of the partners can be quite different just depending on sort of the goals that the consortium has and each individual entity has. We very much try and sort of align individual organization goals with the consortium goals and overall the Australian Space Agency goals.
Yeah, I think that particularly the last one of inspiring and also trying to spread STEM education among a young generation is the one which is most fascinating me, since it's also the way the reason why the Space Info Club started, which is spreading the STEM education and also involving the new generation, also people who are curious about space and would like to know more. So and also thank you for being here today. Because with this podcast, with this episode, we are trying also to contribute to this mission. But I would like to focus on the second goal, which is the one of sustainability, both under the point of view of the business, so in terms of economical sustainability, and also under let's say a wider significance of the word. So how do you envision the sustainability and also the resource utilization, both under the, let's say, environmental point of view? Let's say maybe some people would object to the fact that we are going to the moon just to shrink all the resources to be used for us, and also how the business itself can be sustainable.
Yeah, it's a great question, and I like that you kind of split it into essentially business sustainability and then the environmental sustainability. So I'll start with the environmental side. I mean, what's so fascinating about space and how we can really provide value to Earth is this concept of in situ resource utilization. So it's using the resources that you find wherever you go, where you are. So instead of bringing everything that we need, the oxygen, the water, the building materials from Earth to the moon, using the regolith that exists there that's full of iron, silicon for solar panels, aluminum for building structures, and then water, hydrogen and oxygen for plant growth and breathing, and rocket fuel as well as drinking for the astronauts. That sort of sustainability cycle is really inherent and really required for space, because it's extremely difficult to get things off of Earth. So every added kilogram when you're going from Earth to the moon can add significant amounts of cost. So you want to minimize how much you're bringing with you, which minimizes launch and creates a model that I think the International Space Station, as an example, is the epitome of sustainability. They have a water recovery system that's, I believe, 98% efficient. So their waste is a resource. They're literally only disposing of 2% after it's probably been through the cycle 100 times. So that sort of compact, fully waste integration sustainability technology is being developed for space because, again, it has to be. And I can see a future when we can drive the cost of those sort of systems down, make them more compact, and potentially those are systems that can be in every house, right? That was government-funded research that went to space that has amazing benefits to come back to Earth. And that's just one example. I think there's a lot of those sort of examples where our R&D and investment in space does bring tangible benefit back to Earth. And ISRU is really the focus of this mission. We're trying to understand the resources there so we can better sort of plan in the future of how do we actually develop these, where do we want to put our certain systems, what resources are there versus which do we have to bring so we can build those technologies to drive that sustainability. And then on the commercial side, it's essentially directly a pillar in criteria for trailblazers, the commercial viability. Governments generally across the world don't want to see their funding, their grant funding, which is ultimately taxpayer dollars, turn into nothing, right? They want to be able to sort of provide some grant funding for a particular purpose, but have that be enough sort of funding to drive sustainability in those businesses so they don't have to keep funding these programs. And that's really where the sort of new space race is pivoting, which I think is really beneficial. In the past, it was just governments doing it. And governments are really good at doing something that's never been done before for the first time. NASA and the Apollo program. I'm not sure a commercial company probably could have done that back in the 1960s. But now that they have, commercial companies have been able, like SpaceX for rockets, have been able to drop the cost by multiple orders of magnitude because they can sort of go a bit leaner and find economic use cases within those. And that's what we're trying to do with the rovers here. Take that initial funding to build Australia's capability to build these rovers, but spin those technologies off. For us, mining, for example, is a big focus. What we're building for space at the end of the day is an autonomous lunar excavator. There's a lot of technologies there that are more advanced than what you would see in terrestrial mining. So that's where partners like BHP come in, where we're looking at trying to find the applications of these technologies in their actual mine sites to drive that sustainability.
Yeah, I think that this last point is something that I think few people consider. But before going on, I'd like to give a couple of details for the people who are listening. One is you say that we would need a lot of propellant, for example, to bring things that we want to use over the moon, for example, from Earth. So basically, just to give again people an idea, to put something into orbit, which is, let's say, which weighs a certain amount of kilograms. The percentage of the payload is something like less than 10% of the overall mass of the launcher plus the payload, varying on the basis of the orbit you're considering. And the farther you go, the more propellant you need for the same amount of payload mass. So just consider the terms of the percentages, which is very low compared to the whole amount of propellant. So for sure, this kind of efficiency is needed. And if you don't know how much is 98% of the efficiency in water transportation, for example, or in water generation, think about that our in-house supply of water, for example, can experience up to 70-80% of inefficiency. So in some part of the world, you lose 80 liters of water if you are willing to transport 100. So the efficiency is very low if you think about the waste water that you are on the line, for example. But given these details, just to better put things in perspective, I'd like to focus on the last thing you said, which seems to me a very dynamical approach of both the government and the industry inside this new space economy. Well, maybe a lot of people have always seen the government as a contributor to space research, for example, and when the governmental funding is ended, basically the research ends. But what you were saying, at least to my understanding, is the fact that now the government and the public agencies are a sort of initiator of a process which has to be captured by the industry, who has the role of continuing this process like a sort of a fire, let's say. So the government is the igniter of the fire, but then it's the industry up to continue the process. I don't know if this is correct.
Yeah, I think you summarized it really well there. I think that's certainly a direction that NASA is going, and I see some of the other international space agencies going there, sort of setting the direction, setting the priorities, and providing some of that sort of initial funding to get it going. But in a lot of contracts nowadays, your ability to sort of commercialize the the technology that you're developing for the space agency is being baked into these contracts. So we've covered the Trailblazer one pretty well, but another one, for example, that Lunar Outpost, as lead of the Lunar Dawn team, recently won a contract to design NASA's lunar terrain vehicle. So this will be a large truck-sized vehicle that the Artemis astronauts will be driving. And there's sort of commercialization baked into those contracts too. And again, that's the same model of NASA saying, this is what we want, here's some funding, but commercial industry, you go build it and try and get those costs down, ultimately is what that enables.
Yeah, I think that we have experienced this new approach of NASA also in the last few days, because everyone is basically talking about Boeing Starliner and the comparison with the Dragon SpaceX. The SpaceX Crew Dragon is inevitable, I think, and both the companies have joined the Commercial Crew program by NASA with the same, let's say, business approach, which is a cost-fixed approach. So NASA said, okay, I give you this amount of money, and you have to build your own capsule and make it work with only this money, without additional funding. And I would like to see. I would like to talk about a little. What happens when things don't go as planned? So how risk is managed, and also there are some mitigation strategies under this perspective. Okay, I've taken into account, let's say, a very well-known example. Maybe this is quite bigger than the picture we are looking at today, but I think this makes the idea.
Yeah, risk management is an excellent topic, and it's a really broad one, right? Because we can talk about risk from a technical perspective, obviously, like what happens if the rover breaks or something that goes wrong in the mission. But there's also, programmatic things. What happens if a business can no longer support and or funding stops? There's schedule, cost, all those sort of risks, and that's something that we really considered when, say, building the team. You want complementary efforts, but you want some level of overlap, so you kind of have redundancy in certain systems and capabilities. So there's those sort of risk management techniques and strategies. But to highlight maybe the technical ones, we like to test like we fly is kind of the common saying in the space industry, and one that Lunar Outpost and the ELO 2 consortium really lives by. So we do a lot of prototyping. In stage one, the Australian Space Agency tasked us with delivering a preliminary design of rover, but instead of just sort of doing some analysis and some design, we really wanted to test those things, right? Because you can do as much analysis as you want on paper, but until you actually build the thing and try it, you can't know for certain if something's going to work and or what isn't going to work. So over the course of the past really 15 months, in stage one, we built 4 prototype rovers, each with a specific sort of testing purpose to test things like the low gravity. How can we excavate in this low gravity since no one's done it before? So we built a 1/6 gravity offload model, or 1/6 mass offload model, to replicate as close as we can the forces that you would actually experience while on the moon, and ensure that we can generate enough traction and have enough stability in our mobility systems. We had a separate autonomy prototype just to be testing software, so that we could do that in parallel while working on other things. We had a chassis and suspension model, which is our first one, that helped us sort of put together a mechanical representation and mobility and suspension representation of what this thing is going to actually look like, and start to sort of figure out ways to cut down mass, because again, we're pretty heavily constrained on how much we can bring. And each of those sort of specific testing goals really then fed into the overall prototype, which we call just our consortium prototype, which is a more representative example of what our eventual flight design will look like, as it had representative perception systems, software, electrical, mechanical, mobility, excavation, communications subsystems. So we're able to then simulate mission ConOps. So we actually, we would stay up late at night, so we'd have a dark environment, put in an extreme lighting sort of light bulb to simulate the sun, build craters all around this Regulus simulate sand pits, and then actually test driving the rover without seeing it, so only operating through the cameras, and figuring and sort of confirming some of our assumptions, or figuring out which assumptions are wrong, and then testing the technologies. And that's been really the best mitigation strategy that you can do, is just try it and see what works and doesn't. And that then, it's a very iterative process, informs the next sort of level of design. So we're constantly sort of evolving the design and getting confidence in it as we test those things. So that's our primary mitigation strategy, and I could talk for an hour on all the different tests that we did. But it's really exciting because there's, as I said, there's a lot of layers to the risk management. That's just, does this technology work? Does it not? Does this architecture work? But there's also things like the supply chain. Can we get these components in the time that we need? Can we manufacture them to the quality that we need? All of that is also starting to be mitigated just by building things and testing them. And can the consortium work together? Typically these sort of things may not have as many partners, so there's advantages to having a vertically integrated company like SpaceX and doing it all internal, but there's also advantages to having many partners. But the added challenge with that is all the interfaces that you need between organizations. So again, by trying to build something, we started to establish those interfaces between them. So risk management is really at the core of everything we've been doing for this mission. It's, as I said, is Australia's first lunar rover, and we certainly don't want to see it fail.
For sure. And yeah, I think that you depicted quite a very clear picture. And if there is something that I would like to look from a different perspective, is that it seems to me that we have talked technically so far. So okay, from the logistic point of view, from the technical point of view, so the design, the integration. But at the end of your sentences, you were talking about interfacing with different companies, agencies, and things like that. I think that as it happens in other fields of the industry, when you are interfacing with different businesses, you also need some kind of regulation to correctly interface. Maybe you have to make sure that everyone is, let's say, respecting the contract or is behaving as defining at the beginning. So I would like to go a little deeper into the regulatory environment, and then I will ask you also about the ethics, but this is a secondary question at the moment.
Yeah, regulatory sort of considerations are an interesting topic, and a hot topic.
Maybe not a very funny one, but we have to talk about it.
No, it's important. It's important to ensure that we're going about things the right way, and it's, as I said, sort of a hot topic because it probably depends on who you ask and in which country you ask and what the rules are. To speak for the U.S., there was a Space Resource Exploration and Utilization Act, I believe it's called, in 2015, that enables U.S. entities to engage in commercial space resource extraction activities. So that's the possession, ownership, transport, use, and sale of those resources. But there's a couple different sort of acts. There's the Outer Space Treaty of 1967. That's a little less clear on what you're allowed to do and not do. Overall, you're not allowed to have national appropriation or claim of sovereignty of areas. So it's, if a commercial company starts to mine something, is that a claim of national sovereignty? That's kind of the questions going out there. I think probably no. It's one thing for a country to come in and say, we own the moon. I think generally what the Outer Space Treaty is trying to say is you can't do that. And most countries have signed on to that and agreed. It's a little less clear. And again, they developed this in 1967, so perhaps they didn't have the full vision of what this is sort of now and what we are now envisioning it to be 5, 10, 50 years from now. I think a lot of countries are getting on board with you are allowed to have or conduct space resource extraction activities and do so generally for the betterment of humanity. To actually progress that, Lunar Outpost's first lunar voyage, which will launch in a matter of months, will be conducting the first sale of space resources to NASA. So collecting a very small sample, nothing sort of that will be really utilized. It's more to establish the procedural and legal frameworks for how do you actually conduct a sale, right? Because you have to consider we're not going to collect the material, bring it back, and then sell it on Earth, because the value, as I mentioned with in situ resource utilization, is using it where you find it. So it's doing the sale on the moon, doing it in place sort of transfer of ownership. So the idea of that is we want to just advance that regulatory framework and considerations, with starting with basically a trivial amount of regolith, so that when we go back with larger systems and want to actually start, say, building habitats for the astronauts and using the regolith there, we're not being held up by those regulatory frameworks and who owns this sort of piece of regolith dirt. And we've already kind of figured that out. So there's definitely a lot to kind of be said, and there's whole degrees really just on space resources law and policy on how that works, but it's a pretty interesting consideration.
Yeah, also for the fact that space law is luckily becoming a more popular topic these days. So a lot of people are also trying to take care of this aspect. And I said luckily because we've been used to the fact that usually law comes after the technical aspect, for example, or the operational aspect. So American went to the moon, and then the space law developed around that fact, for example, just to make an example. So also this fact may introduce us to talk about the ethical consideration. You mentioned a lot of very interesting, I think very practical example on how the technology development will help us in the future. And I think this is, at least for me, one of the starting points to talk about ethics of doing space exploration, in particular lunar exploration. So I don't know, what's your view about this topic?
Yeah, I mean, the ethical considerations of it are also an interesting topic. I mean, I'm obviously very on board with it and think that it is a very ethical thing to do. And those that don't, I would encourage to kind of look past the immediate step of, say, putting a rover on the moon. Like, what does that really mean in subsequent steps, and see how that value is actually brought back to the individual and really society on Earth. I think just about every space technology, there's traceability from the investment in that space activity to benefit back on Earth. NASA actually has a really awesome website. Trying to think of the name, but it's something on space technology for the benefit of Earth. NASA. I think if you Google that, you might be able to find their website, but it shows all their different programs and how it's benefiting. Something like the X-ray that was developed by a astrophysicist trying to investigate space, and now obviously we use X-rays all the time, and no one really considers that was a space R&D. Most of the technology in your phones, GPS, everything we really know about climate change and agriculture, all of that is due to space and space investment. And when you start to be able to access resources in space and establish, a literal lunar outpost or actual systems in space, you're driving the cost of all of those things down even further. Our ability to, monitor climate change, if we're able to build satellites in space, that's a significantly cheaper cost in the long run than building them in Earth and launching them from Earth, because then you're also reliant on the launch vehicles. So when you really kind of take a holistic view, even though activity is being done in space, the benefit is still being sought or seen on Earth. And I think there's some AI generated or artist renditions of what the moon would look like if we start mining it, and I can generally say most of those are wrong. If you're imagining looking up at the sky just with your naked eye and seeing a massive mine on the moon, that's not what it's going to look like. There's a lot of asteroids out there as well that provide a lot of excellent resources, and most of what I've talked about is using those resources in place. But once you've sort of established the infrastructure in space, there's potential in the future to bring some of those critical resources back to Earth. Things like platinum group metals or helium-3, things that are more rare on Earth, that are in extremely low concentrations, where we do have to mine massive amounts of Earth material on Earth just to access a tiny bit of this, say, rare platinum group metal, where that may be abundant on an asteroid in space. So longer term, we can basically reduce the amount of mining on Earth, and thus environmental impact on Earth, by building those things in space. And the last thing I'll say, with regards to that is, I think Jeff Bezos has a really good quote with regards to Amazon. Amazon, it was only possible because the U.S. government's investment in the highway system, in infrastructure. When the government invested in building this highway network, they weren't building it for something like Amazon. Amazon just happened to be one of the largest companies in the world, most successful companies in the world. That was sort of an aftereffect due to that investment. By building the infrastructure in space, we're essentially building the highway network, and who knows what sort of benefits can come after that.
Yeah, I think that this is a very, very clear example of the development, the future development, and also how we can look at the future. But it seems that, me first, I'm very curious about, okay, let's try to make this future a little closer to us. So maybe you'd like to tell us a little more about the next timeline, and maybe a roadmap, if it's available or shareable with us of your project. Okay, I have understood that at the beginning you said you're at the very end of phase 1, and you are waiting for next month for phase 2. But what's next?
Yeah, great question. So I'll start with sort of Lunar Outpost as a whole. As I mentioned, our company's first mission is actually flying in a couple months. So it'll be the first commercial rover to the lunar South Pole. And I think that will really mark sort of the domino effect of missions to the moon, and then we essentially have a cadence of a mission every year after that. So then we'll have our second mission in 2025, going to an equatorial region called Orion Gamma, doing some science for NASA there. We then have a third mission in late 2025 with another international space agency, and then the Trailblazer mission, if we're successful, we would launch again around 2027. So for Trailblazer specifically, we're at the end of stage 1. Stage 2 would be kicked off later this year in about 2 to 3 months, and would last about 3 years to finish the design, build, test, and then actually run the mission. And that then really kicks off sort of the space resources utilization and ISRU side of things for the moon, which is also really exciting. And then there's plenty of missions sort of being filtered in throughout there from other agencies internationally and other commercial entities. And I think from that, the most valuable thing we're getting in these first couple missions is the data, right? We're not sending the material back. It's the data to inform these future missions that then start to bring the astronauts. Where do we want to send the astronauts? And then start to actually extract, say, the oxygen that they're going to breathe, rather than bringing that with them. So then that's kind of, as I see phase 2 with the Artemis program, they're gearing up to be able to send those astronauts pretty soon. And the first missions may be on the order of days to weeks, but then the subsequent missions, they may be able to start to stay for months, potentially years, and the ultimate goal is indefinitely. But we need these rover missions first to basically ensure that we can supply things like, again, the oxygen. And then that's where those larger vehicles like the Lunar Terrain Vehicle will also start to come into play to move cargo across the moon, move astronauts across the moon, and conduct much larger range, longer time horizon missions.
Yeah, I think that now it's much clearer, and it seems that the job has just started, because I have understood that for the next at least 5 to 10 years you'll be very busy in building something for sure. So good luck, and also congrats for what you're doing so far. And maybe you are already envisioning some technological spin-offs of the project itself. We have talked a little more general so far, but maybe you'd like to mention some of your own project.
Yeah, absolutely. You're right. I mentioned mining is a really good sort of secondary market from space investment, but if you're not familiar with what an underground mine looks like, you can imagine a very dark, generally rugged terrain environments that can have generally extreme temperature swings. As you start to get deep in the earth, it starts to get pretty hot. There's no GPS, sometimes pretty poor communications. All of those things are true of the lunar South Pole. So the technology, like the autonomy systems that we're developing for localization based on local terrain, the rugged and communication systems, the thermal management systems you have to have for space systems to deal with the extreme temperature swings. All of those technologies are directly applicable to mining equipment and mining systems, particularly as we get to harder to reach places when we're mining. Everything in terms of technology nowadays is really reliant on these rare earth metals that we have to mine for. I've seen some stats. Your iPhone, let's say it's something like 60 to 90 different materials or minerals that are present in that, and some of those are extremely rare and only found in really low concentrations. So we have to expand our mining operations to meet up with the growing demand of renewable energy technologies and AI and all this sort of server farms that are needed for all of that. So by spinning again those specific technologies off, you can enable that for cheaper and also remove humans from those environments. That doesn't sound like a very conducive environment for a human to be in. So that's kind of the avenue that we're taking. And there's some avenues within the defense sector too, when you're in really remote locations, operating something, in Australia, let's say in the middle of the outback, you want to be able to sort of control it remotely, potentially from the other side of the world.
Yeah, probably on, as you said, on your side of the world, you are more used to this kind of situation. Here, sometimes in Europe, we can only dream about such desolated lands to be alone. But I think that they are very valuable and again, practical examples of technological utilization for future aspects for sure. So, in conclusion, I'd like to let you talk a little more about your vision of the future. And I've started dreaming inside this conversation some minutes ago. So maybe you'd like to tell us a little more about your future vision.
Yeah, it's a good way to conclude. So I've kind of been talking about it throughout, but to say it, more plainly, there are infinite resources and energy in space. So just kind of ask you to think about what would that look like on Earth if we were able to access and utilize those infinite resources and energy. That longer term means the potential to move heavy industry off of Earth, to have all of our power generation, or most of it, off Earth, where Earth becomes just a sort of haven for living, and we don't have all of the large industry and pollutant emitting systems and industries on Earth. And that is really only enabled by these first couple steps of exploring the moon, starting to establish the ability to do ISRU, and moon acting as sort of a staging place. It's much easier to get off the moon than it is Earth. So if you base operations off the moon out to these asteroids or even onto Mars, the cost of these efforts is drastically reduced. And then you can, again, use those materials to build these heavy industry sort of factories out in space, where you're not within the atmosphere. That's essentially the key. So it's all really for the betterment of Earth and humanity, and its future. I'm really excited to be pushing towards and be a part of.
Sure, and I'm very happy about this vision, and after this conversation, I hope that everyone is willing to give his or her contribution to this cause, because I think that after today's conversation, it's very clear that we need space and we need to keep exploring and also get into the future. So I'd like to thank you a lot, Joseph, for being here today. It was a very enjoyable conversation. Thank you so much.
Yeah, thank you. I really enjoyed chatting with you as well. It's always fun to talk about this.